Sound. Objectives. State what the source of sound is. Describe the movement of sound through air. Compare the transmission of sound through air with that through solids, liquids, and a vacuum. Describe factors that affect the speed of sound. Describe loudness and sound intensity. Describe natural frequency. Describe the purpose of a sounding board in a stringed musical instrument. Describe resonance. Describe how sound waves interfere with one another. Describe beats. The big idea. Sound is a form of energy that spreads out through space. When a singer sings, the vocal cords in the singer's throat vibrate to and fro, causing adjacent air molecules to vibrate. This air, in turn, vibrates against neighboring air molecules. A series of ripples in the form of a longitudinal wave travels through the air. The frequency of the ripples matches the frequency of the singer's vibrating vocal cords. When the ripples hit your eardrums, the eardrum is pushed and then pulled with the same frequency as the singer's vibrating vocal cords. Vibrations in the eardrum send rhythmic electrical impulses into your brain. And you hear the voice of the singer. Molecules of air behave like tiny table tennis balls. If you place a tuning fork in the middle of the room and then strike the tuning fork with a rubber hammer, the prongs of the vibrating tuning fork set the surrounding air molecules into motion in the same way that the moving paddle sets the table tennis balls into motion. What is acoustical interference? 1. Strike a tuning fork with a rubber hammer or the heel of your shoe. Do not strike the tuning fork on the edge of the table. Place the vibrating tuning fork near your ear. Slowly rotate the tuning fork. Make certain that you rotate the tuning fork through 360 degrees. Observing. What do you hear as you rotate the tuning fork? Predicting. What do you think you would hear if you were to use a tuning fork with a higher pitch, a lower pitch? Making generalizations. What causes the changes in sound intensity produced by rotating a tuning fork? 26.1. The origin of sound. All sounds originate in the vibration of material objects. In a piano, violin, or guitar, a sound wave is produced by vibrating strings. In a saxophone, by a vibrating reed. In a flute, by a fluttering column of air at the mouthpiece. The prongs of a tuning fork in 26.1 vibrate when the fork is struck. Your voice results from the vibrations of your vocal cords. In each of these cases, the original vibration stimulates the vibration of something larger or more massive, the sounding board of a stringed instrument, the air column within a reed or wind instrument, or the air in the throat and mouth of a singer. Figure 26.1. The source of all sound waves is vibration. This vibrating material then sends a disturbance through a surrounding medium, usually air, in the form of longitudinal waves. Under ordinary conditions, the frequency of the sound waves produced equals the frequency of the vibrating source. We describe our subjective impression about the frequency of sound by the word pitch. A high-pitched sound like that from a piccolo has a high vibration frequency, while a low-pitched sound like that from a foghorn has a low vibration frequency. A young person can normally hear pitches with frequencies from 20 to 20,000 hertz. As we grow older, our hearing range shrinks, especially at the high frequency end. Sound waves with frequencies below 20 hertz are called infrasonic, and those with frequencies above 20,000 hertz are called ultrasonic. We cannot hear infrasonic or ultrasonic sound waves. Dogs can hear frequencies of 40,000 hertz, Bats can hear sounds of over 100,000 hertz. Concept check. What is the source of all sound? 26.2. Sound in air. Clap your hands and you produce a sound pulse that goes out in all directions. The pulse vibrates the air somewhat as a similar pulse would vibrate the coiled spring shown in figure 26.2. Each particle moves back and forth along the direction of the motion of the expanding wave. When you quickly open the door, as in figure 26.3a, you can imagine the door pushing the molecules next to it away from their initial position and into their neighbors. Neighboring molecules in turn push into their neighbors and so on, like a compression wave moving along a spring until the curtain flaps out the window. A pulse of compressed air has moved from the door to the curtain. Figure 26.2, a compression travels along a spring. 26.3, opening and closing a door pushes compressions and rarefactions. A, when the door is open, a compression travels across the room. B, when the door is closed, a rarefaction travels across the room. This pulse of compressed air is called a compression. When you quickly close the door, as in figure 26.3b, the door pushes neighboring air molecules out of the room. This produces an area of low pressure next to the door. Neighboring molecules then move into it, leaving a zone of low pressure behind the door. We say the air in this zone of lower pressure is rarefied. Other molecules farther from the door in turn move into these rarefied regions, resulting in a pulse of rarefied air moving from the door to the curtain. This is evident when the low pressure air reaches the curtain, which flaps inward. This pulse of low pressure air is called a rarefaction. For all wave motion, it is not the medium that travels across the room, but a pulse that travels. In both cases, the pulse travels from the door to the curtain. We know this because in both cases, the curtain moves after the door is opened or closed. If you swing the door open and closed in periodic fashion, you will set up a wave of periodic compressions or rarefactions that will make the curtain swing in and out the window. On a much smaller but more rapid scale, this is what happens when a tuning fork is struck, or when the speaker in figure 26.4 produces music. As a source of sound vibrates, a series of compressions and rarefactions travels outward from the source. 26.4, the vibrating cone of the speaker produces the pleasing sound of music. The vibrations of a tuning fork and the waves it produces are considerably higher in frequency and lower in amplitude than in the case of the swinging door. You don't notice the effect of sound waves on the curtains, but you are well aware of them when they meet your sensitive eardrums. Consider sound waves in the tube shown in figure 26.5. For simplicity, only the waves that travel in the tube are shown. When the prong of the tuning fork next to the tube moves towards the tube, a compression enters the tube. When the prong swings away, in the opposite direction, a rarefaction follows the compression. Figure 26.5, compressions and rarefactions travel from the tuning fork through the tube. It is like the table tennis paddle moving back and forth in a room packed with table tennis balls. As the source vibrates, a series of compressions and rarefactions is produced. Concept check. How do sound waves travel through air? 26.3. Media that transmit sound. Most sounds you hear are transmitted through the air, but put your ear to the ground as Native Americans did, and you can hear the hoofbeats of distant horses through the ground before you can hear them through the air. More practically, put your ear to a metal fence and have a friend tap it far away. The sound is transmitted louder and faster by the metal than by the air. Sound travels in solids, liquids, and gases. Or click two rocks together underwater while your ear is submerged. You'll hear the clicking sound very clearly. If you've ever been swimming in the presence of motorized boats, you've probably noticed that you can hear the boat motors much more clearly underwater than above water. Solids and liquids are generally good conductors of sound, much better than air. The speed of sound differs in different materials. In general, sound is transmitted faster in liquids than in gases, and still faster in solids. The boy in figure 26.6 cannot hear the ringing bell when air is removed from the jar because sound cannot travel in a vacuum. The transmission of sound requires a medium. If there is nothing to compress and expand, there can be no sound. There may still be vibrations, but without a medium, there is no sound. Concept check. What media transmit sound? Figure 26.6. Sound can be heard from the ringing bell when air is inside the jar, but not when the air is removed. 26.4. Speed of sound. Have you ever watched a distant person chopping wood or hammering and noticed that the sound of the blow takes time to reach your ears? You see the blow before you hear it. This is most noticeable in the case of lightning. You hear thunder after you see the lightning. These experiences are evidence that sound is much slower than light. The speed of sound in a gas depends on the temperature of the gas and the mass of the particles in the gas. The speed of sound in dry air at 0 degrees Celsius is about 330 meters per second, or about 1,200 kilometers per hour, about 1/1,000,000th the speed of light. Water vapor in the air and increased temperatures increase the speed slightly. This makes sense, for the faster moving molecules in warm air bump into each other more often and therefore can transmit a pulse in less time. For each degree increase in air temperature above 0 degrees Celsius, the speed of sound in air increases about 0.6 meters per second. So in air at normal temperature, about 20 degrees Celsius, sound travels at 340 meters per second. The speed of sound in a gas also depends on the mass of its particles. Lighter particles such as hydrogen molecules and helium atoms move faster and transmit sound much more quickly than heavier gases such as oxygen and nitrogen found in air. The speed of sound in a solid material depends not on the material's density, but on its elasticity. How far away is a storm if you note a 3-second delay between a lightning flash and the sound of thunder? For a speed of sound in air of 340 meters per second, the distance is 340 meters per second times 3 seconds, which equals about 1,000 meters or 1 kilometer. Elasticity is the ability of a material to change shape in response to an applied force and then resume its initial shape once the distorting force is removed. The speed of sound in a material depends on the material's elasticity. Steel is very elastic. Putty is inelastic. In elastic materials, the atoms are relatively close together and respond quickly to each other's motions, transmitting energy with little loss. Sound travels about 15 times faster in steel than in air, and about 4 times faster in water than in air. Concept check. What determines the speed of sound in a medium? Ultrasound imaging linked to technology. A technique for harmlessly seeing inside a body uses high-frequency sound, ultrasound, instead of X-rays. Ultrasound that enters the body is reflected more strongly from the outside of an organ than from its inside, and we get a picture of the outline of the organ. When ultrasound is incident upon a moving object, the reflected sound has a slightly different frequency. Using this Doppler effect, a physician can see the beating heart of a developing fetus that is only 11 weeks old. 26.5. Loudness. The intensity of a sound is proportional to the square of the amplitude of the sound wave. Sound intensity is objective and is measured by instruments. Loudness, on the other hand, is a physiological sensation sensed in the brain. It differs for different people. Loudness is subjective, but it is related to sound intensity. The unit of intensity for sound is the decibel, dB, after Alexander Graham Bell, inventor of the telephone. The oscilloscope shown in figure 26.7 measures sound. Figure 26.7. The loudspeaker at the left is a paper cone that vibrates in rhythm with an electrical signal. The sound sets up similar vibrations in the microphone, which are displayed on the screen of the oscilloscope. The wave on the oscilloscope reveals information about the sound. Some common sources of sound levels are given in Table 26.1. Starting with 0 at the threshold of hearing for a normal ear, an increase of each 10 decibels means that sound intensity increases by a factor of 10. A sound of 10 decibels is 10 times as intense as sound of 0 decibels. 20 decibels is not twice, but 10 times as intense as 10 decibels, or 100 times intense as the threshold of hearing. A 60 decibel sound is 100 times as intense as a 40 decibel sound. Roughly, the sensation of loudness follows this decibel scale. We hear a 100 decibel sound to be about as much louder than a 70 decibel sound, as the 70 decibel sound is louder than the 40 decibel sound because there is a 30 decibel difference between the pairs of sound each time. Physiological hearing damage begins at exposure to 85 decibels. The extent of damage depends on the length of exposure and on frequency characteristics. A single burst of sound can produce vibrations intense enough to tear apart the organ of Corti, the receptor organ in the inner ear. Less intense but severe noise can interfere with cellular processes in the organ and cause its eventual breakdown. Unfortunately, the cells of the Corti do not regenerate. Notes: the decibel scale for loudness is logarithmic. What is the difference between sound intensity and loudness? 26.6. Natural frequency. Drop a wrench and a baseball bat on the floor and you hear distinctly different sounds. Objects vibrate differently when they strike the floor. Tap a wrench and the vibrations it makes are different from the vibrations of a baseball bat or of anything else. When an object composed of an elastic material is disturbed, it vibrates at its own special set of frequencies, which together form its special sound. We speak of an object's natural frequency, which is the frequency at which an object vibrates when it is disturbed. An object's natural frequency depends on the elasticity and shape of the object. The bells shown in 26.8 and tuning forks vibrate at their own characteristic frequencies. Interestingly enough, most things, from planets to atoms and almost everything else in between, have a springiness to them and vibrate at one or more natural frequencies. A natural frequency is one at which minimum energy is required to produce forced vibrations. It is also the frequency that requires the least amount of energy to continue this vibration. What happens when an elastic material is disturbed? 26.8. The natural frequency of the smaller bell is higher than the bigger bell, and it rings at a higher pitch. 26.7. Forced vibration. When you strike an unmounted tuning fork, the sound it makes is faint. Strike a tuning fork while holding its base on a tabletop, and the sound is relatively loud. Why? It is because the table is forced to vibrate, and its larger surface sets more air in motion. The tabletop becomes a sounding board and can be forced into vibration with forks of various frequencies. This is a case of a forced vibration. A forced vibration occurs when an object is made to vibrate by another vibrating object that is nearby. The wash tub in figure 26.9 serves as a sounding board. Figure 26.9. When the string is plucked, the wash tub is set into forced vibration and serves as a sounding board. Sounding boards are an important part of all stringed musical instruments because they are forced into vibration and produce the sound. The vibration of guitar strings in an acoustical guitar would be faint if they weren't transmitted to the guitar's wooden body. The mechanism in a music box is mounted on a sounding board. Without the sounding board, the sound the music box mechanism makes is barely audible. Concept check. Why are sounding boards an important part of stringed instruments? 26.8. Resonance. Resonance is a phenomena that occurs when the frequency of a vibration forced on an object matches the object's natural frequency and a dramatic increase in amplitude occurs. Resonance means to resound or sound again. Putty doesn't resonate because it isn't elastic, and a dropped handkerchief is too limp. An object resonates when there is a force to pull it back to its starting position and enough energy to keep it vibrating. A common experience illustrating resonance occurs on a swing like the one shown in 26.10. 26.10. Pumping a swing in rhythm with its natural frequency produces larger amplitudes. When pumping a swing, you pump in rhythm with the natural frequency of the swing. More important than the force with which you pump is the timing. Even small pumps or even small pushes from something, if delivered in rhythm with the natural frequency of the swinging motion, produces large amplitudes. A common classroom demonstration of resonance uses a pair of tuning forks adjusted to the same frequency and spaced about a meter apart. When one of the forks is struck, it sets the other fork into vibration as shown in figure 26.11. This is a small-scale version of pushing a friend on a swing. It's the timing that's important. When a sound wave impinges on the fork, each compression gives the prong a tiny push. 26.11. The stages of resonance are shown for a tuning fork, A through E. A. The first compression meets the fork and gives it a tiny and momentary push. I'm going to run this slowly, so take your time. B. The fork bends. C. The fork returns to its initial position just at the time a rarefaction arrives. D. It keeps moving and overshoots in the opposite direction. When it returns to its initial position, the next compression arrives to repeat the cycle. Since the frequency of these pushes correspond to the natural frequency of the fork, the pushes successively increase the amplitude of the fork's vibration. This is because the pushes occur at the right time and are repeatedly in the same direction as the instantaneous motion of the fork. If the forks are not adjusted for matched frequencies, the timing of pushes will be off and resonance will not occur. When you tune your radio set, you are similarly adjusting the natural frequency of the electronics in the set to match one of the many incoming signals. The set then resonates to one station at a time, instead of playing all the stations at once. Resonance occurs whenever successive impulses are applied to a vibrating object in rhythm with its natural frequency. English infantry troops march across a footbridge in 1831. It inadvertently caused the bridge to collapse when they marched into rhythm with the bridge's natural frequency. Since then, it is customary for troops to break step when crossing bridges. Notes: like humans, we parrots use our tongues to craft and shape sounds. Tiny changes in the position of my tongue produce big differences in the sounds I make. The Tacoma Narrows Bridge disaster in 1940, shown in figure 2612, is attributed to wind-generated resonance. A mild 40-mile-per-hour wind gale produced a fluctuating force that resonated with the natural frequency of the bridge, steadily increasing the amplitude over several hours until the bridge's collapse. Concept check: what causes resonance? Figure 2612. In 1940, 4 months after being completed, the Tacoma Narrows Bridge in the state of Washington was destroyed by a 40-mile-per-hour wind. 26.9. Interference. Sound waves, like any waves, can be made to interfere. A comparison of interference for transverse waves and longitudinal waves is shown in figure 2613. For sound, the crest of a wave corresponds to a compression, and the trough of a wave corresponds to a rarefaction. In either case, when the crests of one wave overlap the crest of another, there is constructive interference and an increase in amplitude, or when the crest of one wave overlaps the trough of another wave, there is destructive interference and decrease in amplitude. Figure 2613. Both transverse and longitudinal waves display wave interference when they are superimposed. A. Two identical transverse waves in phase produce a wave of increased amplitude. B. Two identical longitudinal waves in phase produce a wave of increased amplitude. C. Two identical transverse waves that are out of phase destroy each other. And D. Two identical longitudinal waves are out of phase and destroy each other. When constructive interference occurs with sound waves, the listener hears a louder sound. When destructive interference occurs, the listener hears a fainter sound, or no sound at all. The listener in figure 2614a is equally distant from two sound speakers that simultaneously trigger identical sound waves at constant frequency. The listener hears a louder sound because the waves add. The compression and rarefaction arrive in phase, that is, in step. In figure 2614b, the listener moved to the side, so the paths from the speaker differ by a half of wavelength. The rarefactions from one speaker reach the listener at the same time as the compressions from the other. Figure 2614, the sound waves from two speakers interfere. A, waves arrive in phase, and B, waves arrive out of phase. It's like the crest of one water wave exactly filling in the trough of another water wave. Destructive interference. If the speakers emit many frequencies, not all wavelengths destructively interfere for a given difference in path lengths. Destructive interference of sound waves is usually not a problem because there is enough reflection of sound to fill in canceled spots. Nevertheless, dead spots are sometimes evident in poorly designed theaters and gymnasiums, where sound waves reflected off walls interfere with unreflected waves to form zones of low amplitude, often moving your head a few centimeters in either direction can make a noticeable difference. Destructive sound interference is a useful property in anti-noise technology. Noisy devices such as jackhammers are being equipped with microphones that send the sound of the device to electronic microchips. The microchips create mirror image wave patterns of the sound signals. For the jackhammer, this mirror image sound signal is fed to earphones worn by the operator. Sound compressions or rarefactions from the hammer are neutralized by mirror image rarefactions or compressions in the earphones. The combination of signals neutralize the jackhammer noise. Noise-canceling earphones shown in figure 2615 are already commonplace for pilots. Some automobiles enjoy quiet rides due to noise cancellation. Noise-detecting microphones inside the car pick up engine or road noises. Speakers in the car then emit an opposite signal that cancels out those noises, so the human ear can't detect them. Similarly, the cabins of some airplanes are now quieted with anti-noise technology. Concept check. What are the effects of constructive and destructive interference? 2610, beats. When two tones of different frequency are sounded together, a regular fluctuation in the loudness of the combined sounds is heard. The sound is loud but faint, then loud, then faint, and so on. This periodic variation in the loudness of sound is called beats. Beats are an interesting and special case of interference. Beats can be heard when two different mismatched tuning forks, like the one shown in figure 2616, are sounded together. Because one fork vibrates at a frequency different from the other, the vibrations of the forks will be momentarily in step, then out of step, then in again, and so on. 2616. The interference of two sound sources of slightly different frequencies produce beats. When the combined waves reach your ears in step, say when a compression from one fork overlaps a compression from the other, the sound is maximum. A moment later, when the forks are out of step, a compression from one fork is met with a rarefaction from the other, resulting in a minimum. Notes. A sound wave traveling through the ear canal vibrates the eardrum, which vibrates three tiny bones, which vibrate the fluid-filled cochlea. Inside the cochlea, tiny hair cells convert the pulse into an electrical signal to the brain. Earplugs typically reduce noise by about 30 decibels. The sound that reaches your ears throbs between maximum and minimum loudness and produces a tremolo effect. If you walk side by side with someone who has a different stride, There will be times when you are both in step and times when you are both out of step. Suppose, for example, that you take exactly 70 steps in 1 minute and your friend takes 72 steps in the same minute. Your friend gains 2 steps per minute on you. A little thought will show that you two will be momentarily in step twice each minute. In general, when two people with different strides walk together, the number of times they are in step in each unit of time is equal to the difference in the frequencies of their steps. What is the beat frequency when a 262 Hz and a 266 Hz tuning fork are sounded together? A 262 Hz and a 272 Hz. Two problems in one. The 262 and the 266 forks produce 4 beats per second. That is 4 Hz. The tone heard will be halfway between 264 as the ear averages the frequencies. The 262 and the 272 forks will sound like a tone at 267 beating 10 times per second or 10 Hertz, which some people cannot hear. Beat frequencies greater than 10 Hertz are normally too rapid to be heard. This applies also to a pair of tuning forks. When one fork vibrates 264 times per second and the other vibrates 262 times per second, they are in step twice each second. A beat frequency of 2 Hertz is heard. Beats can be nicely displayed on an oscilloscope. When sound signals of slightly different frequencies are fed into an oscilloscope, graphical representations of their pressure patterns can be displayed both individually and when the sounds overlap. Figure 2617 shows the waveforms for two waves separately and superimposed. Although the separate waves are of constant amplitude, we see amplitude variations in the superimposed waveforms. Careful inspection of the figures show this variation is produced by the interference of the two superimposed waves. Figure 2617. Sinusoidal representations of a 10 Hz sound wave and a 12 Hz sound wave during a 1 second time interval. When the two waves overlap, they produce a composite wave with a beat of 2 Hz. Maximum amplitude of the composite wave occurs when both waves are in phase, and minimum amplitude occurs when both waves are completely out of phase. Like the walkers in the previous example, the waves are in step twice each second, producing a beat frequency of 2 Hz. The 10 and 12 Hz waves chosen for convenience here are infrasonic, so they and their beats are inaudible. Higher frequency audible waves behave exactly the same way and can produce audible beats. If you overlap two combs of different teeth spacing, as shown in figure 2618, you'll see a moire pattern that is related to beats. The number of beats per length will equal the difference in the number of teeth per length for the two combs. Beats can occur with any kind of wave and are a practical way to compare frequencies. Figure 2618. The unequal spacing of the comb produce a moire pattern that is similar to beats. To tune a piano tuner listens for beats produced between a standard tuning fork and a particular string on the piano. When the frequencies are identical, the beats disappear. The members of an orchestra tune up by listening for beats between their instruments and a standard tone produced by an oboe. Concept check. What causes beats? Noise and your health. science, technology, and society. Most of us try to protect our eyes from excess light, but few give the same care to our ears. Near loudspeakers during her first time at a concert, Allison was alarmed at the pain in her ears. Her friend meant to reassure her when they told her she'd get used to it. But what they didn't tell her was that after the fine tuning of her ears was blasted, she wouldn't know the difference. Industrial noises is even more damaging to the ears than amplified music because of its sudden high energy peaks. Loud motorcycles, jackhammers, chainsaws, and power tools not only produce steady, high volume sound, but also produce sporadic peaks of energy that can destroy tiny hair cells in the inner ear. When these tiny sensory cells in the inner ear are destroyed, they can never be restored. Noise-induced hearing loss is insidious. Fortunately for music devotees, damage caused by energetic peaks is somewhat limited by an inadequate response of electronic amplifiers and loudspeakers. Similarly, for live music, where most of the sound comes from amplifying equipment. If amplifying equipment were more responsive to sudden sound bursts, hearing loss at concerts would be more severe. The impact of hearing loss isn't fully apparent until compounded by age. Today's young people will be tomorrow's old people, probably the hardest of hearing ever. Start now to take care of your ears and prevent further hearing loss. Critical thinking. Describe some situations you might find yourself in that could cause hearing loss. What can you do to protect your hearing? All sounds originate in the vibrations of material objects. As a source of sound vibrates, a series of compressions and rarefactions travels outward from the source. Sound travels in solids, liquids, and gases. The speed of sound in a gas depends on the temperature of the gas and the mass of the particles in the gas. The speed of sound in a material depends on the material's elasticity. An object resonates when there is a force to pull it back to its starting position and enough energy to keep it vibrating. When constructive interference occurs with sound waves, the listener hears a louder sound. When destructive interference occurs, the listener hears a fainter sound or no sound at all. Sound intensity is objective and is measured by instruments. Loudness, on the other hand, is a physiological sensation sensed in the brain. When an object composed of elastic material is disturbed, it vibrates at its own special set of frequencies, which together form its special sound. Sounding boards are an important part of all stringed musical instruments because they are forced into vibration and produce the sound. When two tones of slightly different frequency are sounded together, a fluctuation in the loudness of the combined sound is heard. The sound is loud, then faint, then loud, then faint, and so on.